Hello everyone, I am Lynn Gao. In this presentation, we'll discuss the paper Service Function Chain Placement in Cloud Data Center Networks, a cooperative multi-agent reinforcement learning approach. This paper was written collaboratively with Dr. Yutian Chen from California State University, Long Beach, and Dr. Tang from California State University, Dominguez Hills. In this presentation, we will first start with an introduction going over service function chains, or SFC, and the SFC placement problem. We will then go over our developed algorithm, the multi-agent reinforcement learning algorithm, or MARL. We will also discuss a dynamic programming algorithm and an optimal exhaustive algorithm. Next, we will compare the three algorithms and evaluate their performance. Finally, we'll conclude and discuss future work. So what is service function chaining? An SFC is an effective service provisioning technique in cloud data centers. It consists of a sequence of virtual network functions, or VNFs, such as firewalls and load balancers. Virtual machine cloud traffic traverses a chain of VNFs in order to achieve security and performance guarantees. One example of an SFC can be found in this picture on the bottom right. We have one starting VM, VM1, and one destination VM, VM2. There are three VNFs in this SFC. 1, the firewall that blocks malicious traffic. 2, the load balancer that helps to avoid network congestion. And 3, the cache proxy that caches network packets for quick data access by other clouds. As we can see here, the placement of the VNFs is not necessarily optimal, and we'll discuss a better placement of the VNFs later. As cloud network resources such as bandwidth and energy are limited in a cloud data center network, one important task for the cloud operator is to install the VNFs at the right location inside the network in order to optimize the cloud traffic, or the user-perceived virtual machine communication delay. This leads us to the SFC placement problem, which is, given a VM flow in the cloud data center and an SFC, how do we place the VNFs of the SFC inside the cloud data center to minimize the communication cost of the VM flow? So this is an example of SFC placement. We will compare two placements, one that is more network efficient than the other. The bottom images show a small cloud data center with 6 switches. There is one VM communication flow, starting at VM1 and ending at VM2. In image A on the left, we can see that the VM flow has to travel through 6 switches in order to access all 3 VNFs, resulting in 6 network hops. In image B on the right, we can see that the VNF placements have been changed, resulting in only having to traverse 3 switches using 2 network hops. Comparing the path taken in A with the path taken in B, we can see that B is more network efficient than A. For simplicity's sake, we assume here that each edge is unweighted, but this is not necessarily the case in many real-world problems, where the network hops can have different costs or delays, which can make these problems more complex. In our paper, we discovered that the SFC placement problem is equivalent to the k-Stroll problem. So what is the k-Stroll problem? In the k-Stroll problem, we are given a weighted undirected graph, a source node S, a destination node T, and an integer k. Our goal in the k-Stroll problem is to find an S to T path, or stroll, of minimum length that visits at least k distinct nodes, not including S and T. In the image on the right, we can see the optimal stroll where k equals 2 with source node S and destination node T. The optimal stroll path is S, D, T, C, T. And when we add up the edge costs in this path, we see that the traversal has a cost of 6. An example of a non-optimal path is S, A, B, C, T. And this path results in a cost of 7, which is greater than the optimal 2-stroll given under the image. The k-Stroll problem itself is NP-hard. The connection between SFC placement and k-Stroll can be seen in SFC placement in fat tree data centers. We used a fat tree as an example, but our algorithm is applicable to all network topologies. We start with one pair of communicating VMs with V, or the start node, at host S of V, and V prime, or the destination node, at host S of V prime. We have one SFC with n VNFs, f sub 1, f sub 2, all the way to f sub n. Our goal is to place the n VNFs in the fat tree in a way that will minimize communication cost. Communication cost is calculated using this equation, C sub C of P. In the image below, the blue solid line shows the path with an optimal VM SFC placement and VM communication, while the red dashed line shows the path with non-optimal SFC placement and VM communication cost. In the blue line, we can see that going from V to V prime takes 6 hops, while the red dashed line shows that going from V to V prime takes 10 hops. By taking the path depicted by the blue line, we can minimize the communication cost between the source and destination hosts. In our paper, we discussed 3 algorithms for SFC placement: the multi-agent reinforcement learning algorithm, or MARL, the dynamic programming algorithm, and the optimal exhaustive algorithm. Our main algorithm, the MARL algorithm, is based on reinforcement learning and Q-learning. In a reinforcement learning system, an agent's decision-making is described by a finite set of states S, a finite set of actions A, a state transition function T, and a reward function R. At a specific state, an agent takes an action to transition to a new state while receiving the corresponding reward, determined by the reward function for that action. The agent maintains a policy that helps it to determine the best action to take based on what state it is in. Q-learning is a type of reinforcement learning that uses value-based methods, which include value functions that help the policy to more accurately choose actions. In Q-learning, the value function is Q of S, A, which is defined as the expected discounted sum of future rewards obtained by taking action A from state S following an optimal policy. The optimal action at any state is the action that gives the maximum Q value. Q values are remembered and updated in a Q table. Other than attributes deriving from reinforcement learning and Q-learning, one important component of our MARL algorithm is the action selection rule. An agent follows this rule to select the node to move to during its k-Stroll learning process, and combines exploration and exploitation of an agent. That is, an agent can reinforce the good evaluation it already knows, as well as explore new actions. Given a certain probability, the agent will choose exploitation and move to node T following this equation. Otherwise, the agent will choose exploration and choose node T following the given distribution P of S, T. This is our MARL algorithm. There are M agents, all of whom start at host S of V. The algorithm takes place in iterations, and each iteration has 2 stages. In the first stage, each agent finds its own k-Stroll following the action selection rule. In the second stage, after each agent has found a k-Stroll, we find the k-Stroll with the smallest cost, and update the rewards and the Q values for all the edges in this k-Stroll. Then we check if the termination condition is met, which is usually after a specified number of iterations or within proximity to path costs given by the DP or optimal algorithms. If the termination condition is met, then we finish the training and the algorithm. If it is not, then we will loop back and start another iteration. The time complexity of this algorithm is big O of n times m times k, where n is the number of episodes, m is the number of agents, and k is the number of VNFs. This is the dynamic programming algorithm, an existing SFC placement algorithm which is based on the observation that although finding the shortest stroll visiting k distinct nodes is NP hard, finding the shortest stroll of k edges can be solved optimally and efficiently using dynamic programming. The time complexity of this algorithm is big O of k times the magnitude of v to the power of 4. Finally, This is the optimal algorithm, also an existing SFC placement algorithm, which enumerates all of the SFC placements and finds the one with minimum cost. The time complexity of this algorithm is big O of the magnitude of V to the kth power. Next, we will compare the performance of these three algorithms with k=4 fat trees. The figure on the left compares the VM communication costs in terms of the number of hops yielded by all three algorithms. We have several observations. First, optimal, as shown in green, performs the best by giving the smallest communication cost. Second, the MARL algorithm performs better than the dynamic programming algorithm in most cases, even though it doesn't have complete knowledge of the data center network like the dynamic programming algorithm does. This demonstrates that the MARL algorithm is indeed an effective SFC placement algorithm. The figure on the right shows the execution time of the three algorithms in log base 10 of the actual execution time. While both the MARL algorithm and the DP algorithm are time efficient, incurring less than 1 second for all the cases or negative log base 10 time, MARL takes around half of the time compared to the dynamic programming algorithm. In contrast, the optimal algorithm takes an enormous amount of time, in the order of hundreds of seconds when k gets large, which translates to greater than 0 and almost reaching 2.5 in log base 10 seconds. This shows that our MARL algorithm achieves comparable communication cost as the existing SFC placement algorithms while using a smaller amount of execution time. Next, we compare the MARL algorithm and the dynamic programming algorithm in a larger scale of k=8 fat tree data centers, as shown in these graphs. We did not include the optimal algorithm in this comparison because the execution time would take too long with k=8. The left graph shows that when varying the number of VNFs k from 6 to 12, the dynamic programming algorithm performs better than MARL when k is relatively small, and the MARL algorithm performs better than the dynamic programming algorithm when k gets large. However, the figure on the right shows that our MARL algorithm has a much smaller amount of execution time than the dynamic programming algorithm. In particular, while our MARL algorithm takes less than 1 second or a negative value of log base 10 seconds to find the SFC placement, the dynamic programming algorithm takes hundreds of seconds to do so, which results in log base 10 values that are greater than 2. In a k-array fat tree, the number of switches is equal to 5/4 times capital K squared, capital K being the number of core switches. As the time complexity of the dynamic programming algorithm is originally big O of k times the number of vertices to the fourth, the time complexity of the dynamic programming algorithm in a k-array fat tree is thus big O of k times capital K to the eighth. On the other hand, the time complexity of our MARL algorithm is big O of n times m times k, which becomes big O of n times capital K to the third times k after plugging in the number of switches in a k-array fat tree. We can see that our MARL algorithm is less dependent on the sizes of the fat tree than the dynamic programming algorithm is. Through the time complexity and result graphs of the two algorithms, we can see that the two orders of magnitude difference in execution times show that our MARL algorithm is a promising technique for the SFC placement problem. Another reason why our MARL algorithm performs better can be attributed to the large number of agents that participate in the MARL algorithm. As all the agents work cooperatively and synchronously to learn the state action queue table and make progress towards finding the k-Stroll, the results take less time. Finally, we take a close look at the reinforcement learning algorithm and investigate the effects of the number of agents m in a capital K=6 data center. We fix the number of VNFs k as 10 in all cases. This table shows that with the increase of the number of agents m, the VM communication costs found by the algorithm, the execution time, and the number of training iterations for the algorithm all decrease. As more agents participate, the efficiency of the learning process will increase and become more powerful. We also observed that the VM communication cost seems to stabilize when m reaches 20. One possible reason could be that when m equals 20, the reinforcement learning algorithm is able to find the optimal VM communication cost. In conclusion, we have found that the core of the SFC placement problem is the k-Stroll problem. And under the k-Stroll modeling of SFC placement, deep reinforcement learning is not necessary, allowing us to solve the SFC placement problem using a multi-agent reinforcement learning algorithm, which outperforms existing work. We have 3 research directions in the future. First, we will investigate the convergence and convergence speed of our MARL algorithm by studying the unique discrete structure of k-Stroll. We can go about this by looking at the existing dynamic programming-based algorithm, which provides some insights into how visiting k distinct nodes is related to visiting k plus 1 distinct edges. Second, in our current multi-agent scenario, all the agents cooperate with each other by sharing the same award and updating the same queue table. We are interested in seeing how agents can balance cooperation with competition to find a near-optimal SFC placement efficiently in a rational and game-theoretical environment, wherein different agents have different goals and rewards. Finally, we plan to consider multiple VM flows in the cloud data center. Thank you.